Hello, and welcome to another assignment video walkthrough. In this video, we're going to talk about problem number 8 in section 3.8 for Math 201 Calculus at Morton College. I am Professor Spaniel, your instructor for this course. So for this problem, it says water is flowing at a rate of 50 meters cubed per minute from a shallow concrete canonical reservoir with the vertex down of base radius 45 meters and height 5 meters. And they want us to first find how fast in centimeters per minute is the water level falling when the water is 3 meters deep, and then how fast is the radius of the water surface changing then, and also answer in centimeters per minute. So a good starting place for this is to draw a picture. So what this would be is a fairly shallow canonical basin, so a cone, right? It looks something like this, with a radius of 45 meters and a height of 5 meters. Okay. And so water is leaving this at a rate of 50 meters cubed per minute. Okay. And so this means, so the information we're given here, we've got all this information. We know that the rate at which the water is leaving is constant, and it's 50 meters cubed per minute. Okay, so that is our derivative of the volume with respect to time, right? The volume, meters cubed, is changing at a rate of some time, in this case minutes. So that's 50 minutes cubed, and it should be negative because it's leaving it, so it's a negative rate. So that means we probably need a formula involving volume, and a cone would be a good place to start. So one formula we need for this problem is the formula volume equals 1/3 pi r squared h. Okay, so that's the formula for the volume of a cube. Another formula we need is the fact that radius and height of a cone are directly related, have a direct variation with one another. So that means right now the ratio of the radius to the height of the cone is 9, right? The radius is 9 times the height, and that will never change. That ratio will always be the same. So that means we get the equation r equals 9h. Okay, and in this case, what we're going to want to know is we want to know at what level is the water level falling. So that's going to be dh dt, right? The rate at which the height is changing. And then we also want to know the rate at which the radius is changing. So that's dr dt. So those are the two things we're looking for. So what we want to do now is we want to introduce these rates, dh dt, dv dt, and dr over dt, into our two equations here. Okay, so those are the two equations we have. And so to do that, we just want to take the derivatives. Okay, so the derivative, take the derivative of both sides of the first equation. Okay, so on the left-hand side, we just get dv dt, right? The derivative of v with respect to t. On the right-hand side, we're going to have to use the product rule, right? Because we've got two variables here, r and h. So we're going to have to use the product rule. So we're going to do, the product rule says I take the first thing, so that's 1/3 pi r squared times the derivative of the second factor, the second part of the product. So that would be h, plus the derivative of the first part of the product, 1/3 pi r squared, times the second factor, in this case h. And so then we can do those derivatives. So we get 1/3 pi r squared. The derivative of h with respect to t is just dh over dt. The derivative of 1/3 pi r squared with respect to t is 1/3 pi, right, because that's a constant, times 2r, right? The derivative of something squared, you move the exponent on front and reduce the exponent by 1, times the derivative of r with respect to t, h. Okay, and so then we can rewrite this a little just to simplify it. It's dv dt equals 1/3 pi r squared dh dt plus 2/3 pi rh dr dt. Okay, so that's the derivative of our first equation, right? That's the derivative of v equals 1/3 pi r squared. And now we want to do the same thing for our second equation. So the derivative, whoops, I changed colors there. I don't think I want to do that. So let's try. So the derivative with respect to t of r and the derivative with respect to t of 9h. So this one's a lot simpler. This is just the derivative of r with respect to t is dr dt. The derivative of 9h with respect to t is 9 dh dt. Okay, so now what we can do is we can start plugging in the information we know. So, if we want to find dh dt, we're probably going to want to use this equation on the right that involves volume to start with. And so now we need to start getting rid of everything in the problem that isn't an h, dh dt, the thing we're looking for. So first of all, we remember that we have the rate at which the water is flowing out, dv dt, is negative 50. So let's plug that in. Right, so negative 50. We can also get rid of this r, right, by remembering that r is equal to 9h. So that'll be, we'll put 9h in for r. dh dt is what we're looking for, so we'll leave that alone. We can once again replace r with 9h. And then we also can replace dr dt with 9 dh dt, right? From this equation over here. So this would be 9 dh dt. Okay, and so now all we have left is the thing we're looking for in h's, and it tells us up here that we want to do this when the water is 3 meters deep. So we want to replace all the h's in the problem with 3's. Okay, so this will be negative 50 equals 1/3 pi times 9 times 3 squared dh dt plus 2/3 pi 9 times 3 times 3 times 9 dh dt. Okay, and so now we can simplify. So 1/3 times 9 times 3 squared is 243 pi dh dt, and 2/3 times 9 times 3 times 3 times 9 is 486 pi dh dt. And now notice those are like terms, so we can combine those together. So we get negative 50 equals 243 pi plus 46 pi is 729 pi dh dt, and then just divide by 729 pi. Okay, so that's so we get, I'm going to flip sides of the equation here just to make it a little easier to read. dh dt equals negative 50 over 729 pi. And then the key here is units. So because this negative 50 is in meters cubed and the 3's are in meters, this is meters per minute. And so now we need to do two more things and then we'll be able to answer this first question. First of all, it says we want to do it in centimeters per minute. So we're going to need to change this to centimeters, and we need to round it to 2 decimal places. So we need to put it in our calculator. So what you want to do to find the decimal is you want to plug in negative 50 over 729. 729 pi meters per minute. We want to change that to centimeters, so we're going to multiply by for every 1 meter. Whoops, sorry. So we're going to use 100. There are 100 centimeters in every 1 meter, so that'll cancel out our meters. And then we want to plug that in our calculator to get our answer as a approximation. And so when we do that, we get 2.18 centimeters per minute for the answer for question part A. Right? So that's our answer for part A. And now we can take our answer from part A to answer part B, right? For part B, we want to know dr dt. Well, we have an equation for dr dt over here that involves dh dt, so we just want to plug in our answer for dh dt into here. Oh, and I'm sorry, I messed something up here. This should be negative, right? 2.18. But then when we plug our answer in, it says falling, so then we can get rid of the negative when we plug our answer in up here. That'll be important for this next one because it doesn't say falling or anything for the next one, so we're probably going to have a negative answer because the radius should be getting smaller. So now we just plug in our answer from below. For dh dt. And so we get dr dt equals is negative 50 over 729. Negative 50 over 81 pi meters per minute. And we convert it. So it'd be negative 50 over 81 pi times 100 over 1. And so that's negative 19.65 centimeters per minute. And that's our answer. So that goes up here, negative 19.65 centimeters per minute. Okay, so that was a fairly complicated, and there was a little bit of geometry you had to know there to be able to solve that one. So hopefully that helped you all out with doing problem number 8 from the video. As always, keep filling out those assignment surveys, and I'll keep making these video walkthroughs.